Hello friends, I hope you are fine. In this video, we are going to read chapter 6 of the book Certificate Physical and Human Geography written by G.C. Leong. Friends, I would like to tell you that we have already uploaded the previous 5 chapters on our channel. You can check it out on the channel homepage. So let us start. The title of the chapter is Landforms of Glaciation. The Ice Age and Types of Ice Masses. During the Pleistocene period or the Ice Ages, about 30,000 years ago, great continental ice sheets covered much of the temperate latitudes. It is estimated that more than 12 million square miles of the northern hemisphere were buried by ice, half of which was in North America and the rest in Europe, Greenland, and the high mountains of Eurasia. The warmer climate that followed caused the ice sheets to retreat. Today, only two major ice caps are still present in Greenland and Antarctica. The former covers an area of 720,000 square miles, while the latter is more than 5 million square miles. They are made up of compact sheets of ice, hardened and crystallized to a depth of over a mile. In Mary Bird Land, Antarctica, the ice cap was measured and found to be more than 40,000 feet thick. Under such a colossal weight, the land sinks gradually. From the central dome of the ice cap, the ice creeps out in all directions to escape as glaciers. The peaks of the loftier mountains project above the surface as nunataks. When the ice sheets reach right down to the sea, they often extend outwards into the polar waters and float as ice shelves. They terminate in precipitous cliffs. When they break into individual blocks, these are called icebergs. While afloat in the sea, icebergs assume a tabular or irregular shape, and only 1/9 of the mass is visible above the surface. They diminish in size when approaching warmer waters and are eventually melted, dropping the rock debris that was frozen inside them on the seabed. Apart from Greenland and Antarctica, glaciation is still evident on the highlands of many parts of the world, which lie above the snowline. This varies from sea level in the polar regions to 9,000 feet in the Alps and 17,000 feet at the equator, as on Mount Kilimanjaro. Permanent snowfields are sustained by heavy winter snowfall and ineffective summer melting and evaporation. Where the slopes are gentle and the hollows are sheltered from both direct sunlight and strong winds, any snow that falls is rapidly accumulated. Part of the surface snow may melt during the day, but by nightfall it is refrozen. This process is repeated until it forms a hard, granular substance known as neve in French or fern in German. Owing to gravitational forces, the nerve of the upland snowfield is drawn towards the valley below. This is the beginning of the flow of the glacier, river of ice. It normally assumes a tongue shape, broadest at the source but becoming narrower downhill. Though the glacier is not a liquid, under the continual pressure from the accumulated snow above, it moves. The rate of movement is greatest in the middle where there is little obstruction. The sides and the bottom are held back by friction with the valley side spurs and the valley floor. If a row of stakes is planted across a glacier in a straight line, they will eventually take a curved shape down the valley, showing that the glacier moves faster at the center than the sides. In the Alps, the average rate of flow is about 3 feet a day. In Greenland, it may be more than 50 feet, but in Antarctica, where there is little heat to melt the ice, glaciers move only a few inches a day. The Altesk Glacier in the Bernese Oberland of Switzerland is 10 miles long, affording some spectacular sights to alpine tourists. Though it is the longest glacier in Europe, it is short compared with those of Alaska and the Himalayas, which measure more than 5 times that length. At the foot of mountain ranges, several glaciers may converge to form an extensive ice mass called a Piedmont Glacier. The best known Piedmont Glacier is the Malaspina Glacier of Alaska, which is 65 miles long and 25 miles wide, covering an area of more than 1,600 square miles. Combined glaciers of such dimensions are now rare, and in most continents only valley or alpine glaciers are seen. Now we are going to read landforms of highland glaciation. Glaciation generally gives rise to erosional features in the highlands and depositional features on the lowlands. Though these processes are not mutually exclusive because a glacier plays a combined role of erosion, transportation, and deposition throughout its course. A glacier erodes its valley by two processes, plucking and abrasion. By plucking, the glacier freezes the joints and beds of the underlying rocks, tears out individual blocks, and drags them away. By abrasion, the glacier scratches, scrapes, polishes, and scars the valley floor with the debris frozen into it. These fragments are powerful tools of denudation. Larger angular fragments cut deep into the underlying rocks, so all glaciated floors bear evidence of striation or scratching. The finer materials smooth and polish the rock surfaces and produce finely ground rock floor. The rate of erosion is determined by several factors such as the velocity of flow, gradient of the slope, and the weight of the glacier, the temperature of the ice, and the geological structure of the valley. The characteristic features of a glaciated highland are as follows. The first one is corrie, cirque, or quam. The downslope movement of a glacier from its snow-covered valley head and the intensive shattering of the upland slopes tend to produce a depression where the fern or neve accumulates. The process of plucking operates on the back wall, steepening it, and the movement of the ice abrades the floor, deepening the depression into a steep, horseshoe-shaped basin called a cirque in French. It is also known as a corrie in Scotland and a quam in Wales. There is a rocky ridge at the exit of the corrie, and when the ice eventually melts, water collects behind this barrier to form a corrie lake or tarn. The second one is arids and pyramidal peaks. When two corries cut back on opposite sides of a mountain, knife-edged ridges are formed called arids, a French word. A well-known British example of an arid is the striding edge on Helvellyn in Westmoreland, where three or more circles cut back together. Their ultimate recession will form an angular horn or pyramidal peak. The Matterhorn of Switzerland is a classic example. The third one is Bergsgrund. At the head of a glacier where it begins to leave the snowfield of a quarry, a deep vertical crack opens up called a Bergsgrund in German or Rimaye in French. This happens in summer when, although the ice continues to move out of the quarry, there is no new snow to replace it. In some areas, not one but several such cracks occur. The Bergsgrund presents a major obstacle to climbers further down where the glacier negotiates a bend or a precipitous slope. More crevices or cracks are formed. You can see here the figure 49. The fourth one is U-shaped glacial trough. The glacier on its downward journey, fed by ice from several quarries like tributaries that join a river, begins to wear away the sides and floor of the valley down which it moves. It scratches and grinds the bedrock, removing any rock debris and surface soil. It tends to straighten any protruding spurs on its course. The interlocking spurs are thus blunted to form truncated spurs, and the floor of the valley is deepened. A valley which has been glaciated takes a characteristic U-shape with a wide, flat floor and very steep sides. After the disappearance of the ice, the deep sections of these long, narrow glacial troughs may be filled with water-forming ribbon lakes such as Loch Ness and Lake Ullswater in Britain. They are sometimes referred to as trough lakes or finger lakes. The fifth one is hanging valleys. The main valley is eroded much more rapidly than the tributary valleys as it contains a much larger glacier. After the ice has melted, a tributary valley therefore hangs above the main valley so that its stream plunges down as a waterfall. Such tributary valleys are termed hanging valleys and may form a natural head of water for generating hydroelectric power. The sixth one is rock basins and rock steps. A glacier erodes and excavates the bedrock in an irregular manner. The unequal excavation gives rise to many rock basins, later filled by lakes in the valley trough. You can see here the figure 50, where a tributary valley joins a main valley. The additional weight of ice in the main valley cuts deeper into the valley floor at the point of convergence, forming a rock step. The series of such rock steps may also be formed due to different degrees of resistance to glacial erosion of the bedrocks. The seventh is moraines. Moraines are made up of the pieces of rocks that are shattered by frost action, embedded in the glaciers and brought down the valley. Those that fall on the sides of the glacier, mainly screes, form lateral moraines. When two glaciers converge, their inside lateral moraines unite to form a medial moraine. The rock fragments which are dragged along beneath the frozen ice are dropped when the glacier melts and spread across the floor of the valley. You see the figure 51 as ground moraine. The glacier eventually melts on reaching the foot of the valley, and the pile of transported materials left behind at the snout is the terminal moraine or end moraine. The deposition of the end moraines may be in several succeeding waves, as the ice may melt back by stages so that a series of resectional moraines are formed. If the glacier flows right down to the sea, it drops its load of moraine in the sea. If sections break off as icebergs, morainic material will only be dropped when they melt. Where the lower end of the trough is drawn by the sea, it forms a deep, steep-sided inlet called fjord, typical of the Norwegian and South Chilean coast. You can see here the figure 52. Now we are going to read the landforms of glaciated lowlands. Landforms of glaciated lowlands are mainly depositional in nature, brought about by both valley glaciers and continental ice sheets. The former leaves behind the eroded materials in only resected areas. The imprint of ice sheets on the landscape is far more widespread because they advanced through large areas during the ice ages, scoring and removing any surface soil and rock debris on their way. As a result, it has been estimated that almost a third of the total land surface of Europe and North America is littered with glacial and fluvio-glacial materials of all descriptions: moraines, boulder, clay, tills, drifts, rock floor, gravels, and sands. Many of them are being re-eroded, resorted, and redeposited elsewhere by present-day rivers. Most of the glaciated lowlands have depositional features, but where rock masses project above the level surface, they result in striking features of erosion, such as the roque montoni and crag and tail. The first one is roque montoni. This is a resistant residual rock hummock. The surface is striated by ice movement. Its upstream side is smoothed by abrasion and its downstream side is roughened by plucking and is much steeper. The term roque montoni is used to describe such a feature because it resembles a sheepskin wig once worn in France. Roches montonis are found in both highland and lowland glaciated regions. The second one is crag and tail. The crag is a mass of hard rock with a precipitous slope on the upstream side, which protects the softer leeward slope from being completely worn down by the oncoming ice. It therefore has a gentle tail strewn with the eroded rock debris. The classic example is the Castle Rock of Edinburgh, Scotland. Edinburgh Castle is located on the crag and the high street on the tail. The remaining glaciated lowland features are of a depositional nature. The following are the typical ones. The third one is boulder clay or glacial till. This is an unsorted glacial deposit comprising a range of eroded materials: boulders, angular stones, sticky clay, and fine rock floor. It is spread out in sheets, not mounds, and forms gently undulating till or drift plains. The landform is rather monotonous and featureless. The degree of fertility of such glacial plains depends very much on the composition of the depositional materials. Some of the boulder clay plains, such as East Anglia and the northern Midwest of USA, form rich arable lands. The fourth one is erratics. These are boulders of varying sizes that were transported by ice. They came with the advancing glaciers or ice sheets, but when the ice melted, they were left stranded in the regions of deposition. They are called erratics because they are composed of materials entirely different from those of the region in which they are found. Such erratics are thus most useful in tracing the source and direction of the ice movement. Sometimes the erratics may be found perched in precarious positions just as the ice dropped them, and they are then termed perched blocks. Examples of such blocks are commonly encountered in both lowland and highland areas in Europe. Example, Silurian grits are found perched on the Carboniferous limestone of the Pennines. Their presence in large numbers is a hindrance to farming. The fifth one is drumlins. These are swarms of oval elongated whale-back hummocks composed wholly of boulder clay. With the elongation in the direction of the ice flow that is on the downstream side, they are low hills varying from a few yards to 400 feet in height and maybe a mile or two long. They appear a little steeper at the onset side and taper off at the leeward end. They are arranged diagonally and so are commonly described as having a basket of eggs topography. Large numbers of them are found in County Down in Northern Ireland and the glaciated plain around the Great Lakes in North America. The sixth one is eskers. These are long, narrow, sinuous ridges composed of sand and gravel which mark the former sites of subglacial meltwater streams. They vary from a few feet to 200 feet in height and may be several miles long. In some parts of Maine, USA, the outstanding eskers form a continuous ridge of 100 miles. They are very numerous in Scandinavia. Example, the Punka Harju esker of Finland, as eskers are made up of highly porous sand and gravel. Water is rapidly drained off from their crest and they may not support many trees. Though in Finland, they often form tree-covered bridges between lakes. The seventh one is terminal moraines. These are made up of the coarse debris deposited at the edge of the ice sheet to form hummocky and hilly country such as the Baltic Heights of the North European plain. The eighth one is outwash plains. These are made up of fluvio-glacial deposits washed out from the terminal moraines by the streams and channels of the stagnant ice mass. The meltwater sort and redeposit the material in a variety of forms, from the low hilly heathlands such as the Luneburg Heath of the North European plain to undulating plains where terraces, alluvial fans, and deltaic deposits of the meltwater streams make up the landscape. Kames, small rounded hillocks of sand and gravel, may cover part of the plain, where the deposition takes the form of alternating ridges and depressions. The latter may contain kettle lakes and give rise to characteristic knob and kettle topography. Now we are going to read the human aspects of glaciated landforms. Though the ice ages were at their height over 30,000 years ago, the effects of glaciation on both landforms and human activities have profound influence in many parts of the world today. Their most striking impact is felt in the temperate regions of Europe and North America, which were once under continental ice sheets. Further south and on the high mountains all over the world, slow-moving glaciers are still shaping the landscape in the Alps, Andes, Rockies, and Himalayas. Glacial influences on man's economic activities are both favorable and unfavorable, depending on the intensity of glaciation, the relief of the region, and whether the effects are of an erosional or depositional nature. In hilly regions, such as the mountain slopes of Scandinavia, ice sheets and glaciers have removed most of the topsoil, leaving them quite bare of vegetation. Soils that do exist are so thin that they are incapable of supporting effective agriculture. Glacial rifts in the valleys and benches or arcs which were not affected by glaciers have good pastures during summer. Cattle are driven up to graze on the grass and return to the valley bottom in winter. This form of animal migration type of farming is called transhumance. Transhumance. Extensive border clay plains such as those of East Angelina and the Midwest of USA are some of the most fertile agricultural plains known. The lowest plains of Europe and central USA with a high proportion of humus are good farming land too. On the other hand, the sandy or gravelly outwash plains, example the heath-covered coast of northern Germany, the marshy border clay deposits of central Ireland, the barren ice-scored surfaces of the Canadian and Baltic shields are infertile. The presence of numerous erratics and perch blocks in parts of Britain and in Alberta, Canada, many of them of gigantic size, obstruct farming and the use of machines. The morainic deposits may dam or glaciers may hollow out lakes which greatly inconvenience large-scale farming or land development. But when the lakes are eliminated, the old glacial lake beds with the rich alluvium support heavy cropping. Large lakes formed by the former glaciation, example the Great Lakes of North America, make excellent waterways. They may also cut deep overflow channels while draining off, making natural routeways across a mountainous terrain. Example, the Hudson-Mohawk Gap that links the interior with the Atlantic seaboard of USA. On the other hand, in regions where drumlins are dominant, the drainage is either poor or much confused. Terminal and recessional moraines comprise coarse materials of little use to man, but fluvio-glacial deposits are not without their economic significance. In the outwash plains, eskers and kames have been excavated to provide sands and gravels for highway and building construction. The purest sands are extracted to make molds for metal castings. The lake basins of glaciated mountains provide natural reservoirs. In countries like Scandinavia, Switzerland and Canada, where there is little available coal, streams and waterfalls that plunge down from hanging valleys or other glaciated uplands are being harnessed to provide hydroelectric power. This has helped to develop many of the chemical and metallurgical industries with the magnificent scenery provided by the glaciated mountains. Example, the French, Italian and Swiss Alps. Large numbers of tourists are attracted to them annually. Skiing, mountain climbing and sightseeing are all popular with alpine tourists. And with this, our chapter ends, and in the next video, we will read chapter 7. So stay tuned, subscribe the channel, press the bell icon and study well. Thank you.